All right, so in this video, we're going to talk about surface area of revolution. So now we're back to needing to take our curve and rotating it around an axis to create that three-dimensional solid of which we'll then find the surface area of. And so you can see the picture that I'm starting off with here. I'm going to go ahead and take this guy around the x-axis. So if I take it around the x-axis, it's going to look something like this. Now, I don't want to draw the entire solid in here just yet, mostly because the picture is going to get unnecessarily messy and prevent us from actually coming up with this formula. So instead, what I'm going to do is I'm going to remind you again that an integral is going to take infinitely small things and add them up. So we're going to use an arc length component and a little bit of geometry. So what I'll start off with here is just taking a couple of these lineal elements here, and let's say here. And you can see that blue stuff is similar to the blue stuff that I had in the last video, where it gave us an opportunity now to talk about one of them and come up with then a general formula for all of them. So when I have those blue things in there, now knowing that it's going around the x-axis, I'm going to have a bunch of these partitions in here, if you will. So something like that. And again, it's a surface area calculation, not a volume calculation. So if I call this maybe P1, P2, P3, then if I want to find the surface area of this, I can now say that the area of our P sub i's, the ith partition, can be found by taking the circumference of this thing multiplied by that arc length component. It's much like finding the area of a cylinder, right? If you take a piece of paper and you roll it up, that's going to be a cylinder. But if you want to find the surface area of it, you're going to have that circumference being the top and the bottom multiplied by the height or the length of the piece of paper. And so it's no different here. We would need our circumference, and we know circumference is our 2 pi r, multiplied by the arc length. So this is our circumference multiplied by the arc length. Now, notice we're going around the x-axis here. So we're going to have a couple different formulas that we need to discuss. If we go around the x-axis, like I have pointed out, then our surface area here can be denoted as the integral from a to b, our 2 pi, the radius. Remember how we did radius earlier? If this guy here was our radius, then we know that that's going to be our f of x. So we have our f of x multiplied by the appropriate arc length formula, the 1 plus dy dx squared dx. And so there's our formula going around the x-axis. But now, let's suppose we want to go around the x-axis with respect to y. Well, we can still do that. We would now have the integral from c to d, pi, but we can't have x's anymore, so this can't be f of x. But conveniently, f of x is equal to y, so we can just throw a y in there and use the appropriate arc length formula now, where we have this dx over dy squared dy. So those are the two formulas now, again, going around the x-axis, one with respect to x, one with respect to y. Now, if we want to go around the y-axis, you're also going to have some formulas for it. Now, I don't feel like I need to draw an entirely different picture because it's the same exact thing, except now we're going this direction and we're going to have a different radius to take into consideration. So for the y-axis, if we want to go with respect to y, which is the easiest case to visualize, we're going to have our 2 pi. Let's say our curve is now g of y, it's got to be a y, square root 1 plus dx dy squared dy. Similar on the bottom one, if we want to go around the y-axis but with respect to x, we're going to be integrating from a to b 2 pi x square root 1 plus dy dx squared dx. Okay, so I would encourage you, especially going around the y-axis, to maybe draw a similar picture. Maybe you'll have an x and a y here. Here's your curve. That's x equals g of y. And if you want to go around this guy, the same idea can be drawn from here into this right here. And once that's drawn, the formula would be the same, and you're just now substituting things in with respect to the other variables as we did in the previous one. So you'll see we have 4 different formulas here to think through before we start a problem as to which one is going to be appropriate for the given information. So it's going to be important to kind of have these laid out in front of you, understand what each of them represents and what information is needed to make them do what they're supposed to do. So let's take a look at a couple examples. Okay, so for this one, we're going to find the surface area of revolution for this curve going around the x-axis on the interval 1 to 2. So given that information, and looking back at those previous formulas we derived, we would want the integral from a to b, a 2 pi f of x square root 1 plus dy dx squared dx. Okay? So most of your work is going to come from this guy right here, which is the same arc length component from the last section. So we'll do it the same way as we did then. We know that dy dx is going to be 3x squared. If I take this thing now and square it, I'm going to end up with a 9x to the 4th. And so to get this thing set up, I'm going from 1 to 2 pi. The f of x right here is going to be our x cubed. And then I have a square root of 1 plus 9x to the 4th dx. And so, again, getting it set up is really not that difficult. You just got to make sure you use the correct formula, and then you're nice and slow and precise with your arc length calculation as you throw that in there. And as I said before, some of these can be a little bit messy because of the complexity of needing to integrate. And these answers can also come out a little bit crazy too, so don't be too surprised when something crazy comes out. This one in particular, if you were to evaluate it, which is a simple U sub, by the way, very simple U sub, let U equal this, it matches up nicely with that, and then it falls apart from there. But the answer is actually kind of crazy. 145 root 145 minus 10 root 10 all over 27 pi. So that's the actual answer that you would get it when you compute it, which the computing the integral is easy. It just might be a little surprising how messy that answer is. So again, pick the right formula, go nice and slow through the arc length computation, and then the rest should take care of itself. Okay, for this example, it's the same basic idea, but now we're taking this curve and we're going around the y-axis. So based upon your given information, you can see how you're given a function solved for y, you're given x interval, but you're going around the y-axis. Looking back at those 4 formulas from earlier, you can see we would want to use the integral from a to b 2 pi x root 1 plus dy dx squared dx. Okay, so I'll need to start with my dy dx, which is going to be an x to the 1/2. I need to square it, which then just gives me the x. So plugging that stuff in, I'll get the integral from 1 to 2 pi, and then I'm just putting an x in right there. And then I have my square root 1 plus x dx. So once again, a pretty simple setup. The integral here is another u sub, but it is one of those wraparound ones where once you let this equal u, you're going to have to circle back and replace that. So you guys can handle that. You've seen several of those before. But again, the answer unexpectedly is a bit messy. The answer here is 8 pi over 15 times 6 root 3 minus root 2. So much like you've seen in the past, these integrals can be a little bit messy, but I believe if the problems are constructed nice, which they have to be at this level, you should still be able to get through them without too much stress.